In this lecture, we're going to derive a specific rule that can be used when differentiating inverse functions. Now, this rule will then be applied to derive formulas for the derivatives of arcsine, arccosine, and arctangent, the inverse trig functions. It's not as important as the chain rule or the product rule, which are used extensively throughout calculus and applications to engineering, physics, etc. But it's still an important rule in its own right. So to start, let's just review the basic notation behind inverse functions and their derivatives. So if we have a function y is equal to f of x, and then of course the derivative dy dx is given by f prime of x. So this is just differentiating of a general function, y is a function of x. Now the inverse function is obtained by basically doing the following. We get x is equal to f inverse of y. So here the inverse function takes a point in the range of f and returns the corresponding point in f's domain. So it goes backwards. And the notation for the derivative, which we explored earlier in chapter 2, was x dy is equal to f inverse prime of y, right? Because this function f inverse is a function in its own right, and therefore you can differentiate it. So as normal, it's just the rate of change of the output. In this case, for f inverse, the output is x with respect to the input y. So it's dx dy. Now comparing the derivative formula for f and the derivative formula for f inverse, well, actually I shouldn't call it a derivative formula, it's just kind of the notational structure of the two. Well, we have dy dx versus dx dy. Now you might be tempted to guess that, well, dx dy should just be the reciprocal of dy dx. And you would be, in this case, correct. So as it turns out, and this is basically the achievement that we're going to do today, we're going to say that dx dy is 1 over dy dx. Now, of course, to be precise about things, it's not entirely as simple as that, though that is the main idea. Well, if this is the reciprocal of this, let's write the following. F inverse prime of y should equal 1 divided by f prime of x. So that is a valid formula, and it's valid for a point x comma y on the graph of f. That is, the output value y needs to be inserted into or plugged into the function f inverse prime, and then the input value x is plugged into the function f prime. Now, in order to have a consistent variable, which will make things more useful, because in general we'll be applying this to say, okay, here's a function that happens to be the inverse of some other function we know, but we're just interested in that function by itself. So we're interested in arcsine of x. What's the derivative of arcsine of x? So we don't want to say the derivative of arcsine of y is 1 over some function of x. So we want to use a common variable. So to do that, we recall that x is equal to f inverse of y. So we're going to replace x with f inverse of y. So corollary of this, f inverse prime of y is equal to 1 over f prime of f inverse of y. So now we have achieved a consistent variable. And then just as a cosmetic enhancement, we can change y to x, because whenever we have a function, the name of the independent variable is really sort of artificial. It's the function f, right? Whether we say f of x, f of w, f of y, f of z, it doesn't matter what we name the independent variable. The name of the independent variable is not a part of the function itself. So here we just have a functional relationship. It looks complicated. F inverse prime of input variable is equal to 1 divided by f prime of f inverse of input variable. So instead of using y's here, let's change the y to an x, because we can call Since it's consistent in both of these, we can just name it however we'd like. So the main result is f inverse prime of some variable x is equal to 1 over f prime of f inverse of x. So this is a derivative rule that you might see written in various textbooks, and that's where it comes from. Now we can, interesting theoretical point, we can actually use the chain rule to derive this as well. I'll show you that in a minute, but first let's do just an example. Okay, so I moved our main equation to the top of the board. Okay, so for an example, let's consider y is equal to x cubed plus 8. So in other words, our function that we're looking at is f of x is equal to x cubed plus 8. Well, first of all, f prime of x is pretty simple. I'll put that up here. F prime of x is just equal to 3x squared. So 1 over f prime of x should just equal 1 over 3x squared, like that. Okay, so now let's look at this formula for the derivative of an inverse function and unravel it step by step. But first, let's actually compute an explicit formula for the inverse function f inverse. So to do that, we start with our equation. We assign the output a variable name, so y is equal to f of x. Right? So remember our chart, y is equal to f of x. So x is going to equal f inverse of y. So we solve this for x. So first of all, we do y minus 8 is equal to x cubed. So therefore x is equal to the cubed root of y minus 8. And this means that, in particular, f inverse of y is going to equal the cubed root of y minus 8. So this is the inverse function. It's f inverse of y is the cubed root of y minus 8. However, oftentimes we want to express our inverse function just as a function of x. So to do that, at the final step, once we have f inverse of y and we only have the variable y on both sides, we can say, well, f inverse of x is equal to the cubed root of x minus 8. So that's just like saying, here's a function of x, and it's the inverse of some other function. So this is the inverse function to the function f of x is equal to x cubed plus 8. Now remember, when we first discussed transformations of functions, we defined the inverse function as the unique function that when you compose it with the original function, we receive x. So remember, it was this f composed with f inverse of x is equal to x. And that's equal to f inverse composed with f of x. So in other words, when you do f of f inverse of x, you should just get x. So to check that out, let's do f composed with f inverse of x. So that's literally f evaluated at f inverse of x. So f evaluated at f inverse, what this means is we're going to have to take f inverse of x and then plug it in for the x wherever we see x in the f equation. So this becomes, well, this thing goes into x. So we have cubed root of x minus 8 cubed. So this is f inverse of x right there, replacing this x right here. So we're going to cube that, and then we're going to add 8. Now, as you can see, this is equal to x, right? If you do the cubed root of something and then we cube it, we just get the something. So it's x minus 8 plus 8 equals x. So that verifies this relationship that this is indeed the inverse function. Same thing with ln of x versus e to the x. E to the ln of x is x. ln of e to the x is x. Right? So ln of x and e to the x are inverse functions of one another, just like the functions x cubed plus 8 and cubed root of x minus 8 are inverse functions. Just like sine and arcsine are inverse functions. Now, how does this tie back into this seemingly complex formula that we started with? Well, let's get some space. Let's see, we don't need that. And I think we can safely omit this. And then let's pull this one up here. Now let's put it right there. And then let's clear off that. Okay, so all right, so we can compute the derivative of f inverse directly. So this would be what you would do without using this formula. So f inverse prime, well, that's no more difficult than just taking the x derivative of this equation. So we have x minus 8 quantity to the 1/3. Recall that the cubed root is just that thing to the 1/3. So it's going to be 1/3 x minus 8. Then we subtract 1 from the exponent, so 1/3 minus 1 is negative 2/3. So we get 1/3 x minus 8 to the negative 2/3 times the derivative of the inside. Now the inside function is just x minus 8, and the derivative of x minus 8 is 1, so we only have to multiply this by 1. And so this is equivalent to 1 divided by 3 x minus 8 to the 2/3. So that was f inverse prime of x. As computed directly, we literally went through all the steps to locate the inverse function, and then we took the derivative of the inverse function. Now oftentimes that can be a strenuous endeavor to undertake, especially if the inverse function is complicated or unwieldy. So this formula as a workaround is a nice thing to have. Now in this case, we didn't need it. The function was simple enough that we obtained an easy inverse function. It's just cube root of x minus 8, easy function to differentiate, and there we go. But it's still a good test to just see that this formula works correctly, because we have the direct way and then the formulaic way to compute this derivative, so we can compare the two and see if they're the same. Now recall I said 1 over f prime of x way back at the beginning was 1 over 3x squared. Well, this doesn't look like 1 over 3x squared. And the reason is because f inverse prime of x is not 1 over f prime of x, it's 1 over f prime of f inverse of x. So f prime of x was 3x squared. So f prime of f inverse of x, I have to take, that's the same, f inverse of x is x minus 8 to the 1/3. That's f prime evaluated at f inverse of x. So it's f prime evaluated at the cubed root of x minus 8. So I have to take the cubed root of x minus 8 and input it into the function f prime. So this x gets replaced with the cube root of x minus 8. So that becomes 3 times the cubed root of x minus 8 squared. Cubed root is that thing to the 1/3, and then to the power 2 becomes 3 times x minus 8 to the 2/3. So therefore 1 over f prime of f inverse of x is equal to 1 over 3 times x minus 8 to the 2/3, which agrees with what we did that way. So the formula is confirmed by or at least validated by this example. The example, you can't actually prove a formula like this using one example, because it could be false in a different case, but it supports our prior claim that this formula is indeed correct. Now there's another way to derive it, which I'll show you briefly in our last few minutes of this video. And that is going back to the chain rule. And going back to the definition of the inverse function. So by definition, f of f inverse of x has to equal x. So that's the defining property of what an inverse function is. So the idea is, okay, well, let's apply the chain rule to actually differentiate this formula. So we have a nice formula here. Now let's apply the chain rule. So in general, the chain rule can be written as follows. When you have f of g of x, the derivative is f prime of g of x times g prime of x. So it's no different here. So the derivative of this is f prime of this, f inverse of x, and then times the derivative of the inside function, which in this case, it's the derivative of f inverse. So it's f inverse prime of x. And that should equal the derivative of x, which is just 1. So I differentiated this equation with respect to x, and I obtained f prime of f inverse of x times f inverse prime of x is equal to 1. So therefore, f inverse prime of x will equal 1 over f prime of f inverse of x. And there's the formula again. So literally this formula can be obtained by simply differentiating this defining formula for an inverse function.